Hey there, boys and girls. It's Mr. Jones, and I'm back with another YouTube learning video. Today, I just want to go over some key concepts related to patterning. We know that patterns can be represented in a variety of ways. They can be expressed in numbers, for example, 5, 7, 9, 11, in a pattern rule, start at 5 and increase by 2 each time, in a model, as shown below, in a graph, also as shown below. However, that graph doesn't represent the pattern that I've been talking about previously, or as an algebraic expression, for example, 2n plus 3. This year we focus on graphing patterns, extending patterns using an algebraic expression, and representing the nth term of a pattern as an algebraic expression. We also focus on extending patterns using a graph as well. So let's start with the basics of patterning. To graph patterns, we need to first put them in a table of values. So here I've done just that. On the left-hand side, in the left column, we have term number, and that just goes sequentially 1, 2, 3, 4, 5, etc. And on the right, we have the term value, which is our actual pattern, and put it into the table. So next, we turn our table into ordered pairs. So you don't actually have to write this part down, but in your head at least, you have to realize that that's the case because you need to plot them on a graph. So you need to realize that your term number is going to be your x value, and your term value is going to be your y value when you graph these values. In this case, we can see that the pattern is a linear pattern because when graphed, it creates a line. The terms increase by a constant amount. Tip: when graphed, the constant of the algebraic expression is the value when x is 0. So we'll talk more about how to figure out what the constant is using other means, but if you've graphed your pattern already and you sort of extrapolate or you connect your line with the y-axis, where it hits when the x-axis is worth 0, that's going to be your constant. Because we can see that the term value is increasing by 2, we can extrapolate to figure out what the value of the sixth term is. So in this case, you can see I've extended my line, and it's actually going beyond the limit, beyond the top of our graph, but you can see that for the sixth term, it would be worth 15, right? And that makes sense with the pattern we have, because at 0, it's 3, 5, 7, 9, 11, 13, and 15. A simpler way to determine the nth term is to use an algebraic expression. But how do we determine what the algebraic expression is for a pattern? First, we'll go over what makes up an algebraic pattern rule or expression. An algebraic expression consists of a variable, a coefficient, and a constant. So the variable is the unknown number that's represented by a letter. In patterning, it's usually n, but often in algebra, we see it represented as x or y, or it could be represented as a or b or c. It could really be any number, any letter. The coefficient is a number that's usually in front of your variable, and it tells you how much to multiply your variable by. And then your constant is a number that's added, or it could possibly be subtracted from the previous term there. That first chunk, the coefficient and the variable, we can call a rate of change when we're talking about patterns. So sort of the two parts that make a pattern are the rate of change and the constant. The rate of change is what we call the part of the pattern that has a multiplicative relationship, right? So it's the part that increases by such and such each time. To figure out the value of a term, you substitute the term number into the equation for n, then evaluate or solve the equation. For example, to find out the value of the 12th term for a pattern that follows the pattern rule before, we would do the following. So the pattern rule we had before was 3n plus 2. When I substitute 12 for n and then evaluate, we end up with 38. I will do a lot more of this when we get into our algebra unit, but as we've gone over in class, this is important for solving for the nth term in patterning. So that's simple enough if you're given the equation that represents a pattern, but what if that's not the case? We can figure it out using a couple of simple tricks. So in order to determine the expression of a linear pattern, we should first figure out the constant, right? So as we know, that's that second part, the number that's either added or subtracted from the rate of change. So first, again, it's a good idea to put our pattern into a table. The next thing we want to do is actually figure out the differences between our term values, right? We call that our first difference. This is important because it tells us how much our pattern is increasing by. You could also figure out the difference between the first differences, but that's sort of advanced, and in this case we really don't need to do it because we can see that our first difference is constant anyways. Once we know that our first difference is 2, we'll subtract that amount from term 1 to sort of get an imaginary term 0. This value is our constant. So again, term 0, that would be the spot where our line hits the y-axis, right? Our y-intercept. And that's going to be our constant for our equation. So in this case, it's 5 minus 2, which is 3. With our constant being 3, we know our expression will end in plus 3. If we get rid of the constant from our first term value, we're left with 2. And so we think to ourselves, what relationship does 2 have with our term number, which is 1 for the first term? And we could say 2 times 1, sorry, that should be an equal sign there, equals 2. This means that our equation is 2n plus 3. We can check by substituting another term number and evaluating. If it gives us the correct term value, our equation is correct. So we'll do that now. So we'll use our second term number, so 2n plus 3, 2 times 2 plus 3, 4 plus 3 gives us 7, and when we check, our term value is indeed 7 for the second term number. So our equation works for both term 1 and term 2. If it's a linear pattern, meaning that the first difference is the same or constant, it will work for the other terms. Alright, so that's it for this video. I hope that helped to explain some of the patterning concepts we've come across so far in this unit. If you have questions, feel free to ask and we can go over it more, or you could suggest another YouTube video that you want me to make below in the comments. Alright, thank you so much for watching.